Okay, welcome to the next session of the array subsystem. So in this session we are going to talk about the other two categories of our hierarchical memory structure, or that is nothing but SAM and CAM. That is more unique when you are going to compare with your normal volatile and non-volatile memory. So let me go one by one to understand. So let me start with the SAM, that is nothing but serial access memory. So when you are going to compare with the normal conventional memory devices, this SAM doesn't have any kind of address. Normally when we see that in the SRAM and DRAM and as well as the even in the ROM read-only memory, we are seeing that there is a row and column structure. Of course here also we will have a row and column structure, but we will make use of this bit line and word line in the SRAM and DRAM to access your row and column. Same way in the DRAM also we are making use of the bit line and word line, yes of course, and as well as in the ROM architecture, read-only memory architecture also we just make use of your the Q0 to Qn minus 1 to be act as a read and write operation, and it acting as your column selector, and as well as for row selectors we have the address lines are available. But in the case of the SAM, there is no need of any kind of address is not required, right? And another one major important element of your SAM is going to be the shift registers. As we discussed at the first sessions, the previous sessions, we seen that it's going to adopt SIPO, right? SIPO and as well as the PASO as one of the structure for your serial access memory, and followed by we are following the first in first out and as well as last in first out as a technique to go for the serial access memory, like queues and stacks. Let me see it later, right? So that is the main things about your uniqueness about the SAM. It doesn't have any address lines as like the conventional memory architectures. Then how it is going to be? So here we are making use of the shift registers to store the data and to have a delaying the data, which if you want to be take it down, and we can make use of the simple design. A cascade of the registers can be done. That is more simple for us to go for framing of your SAM, serial access memory. And here we can just showing the simple architecture of your shift register. I hope this we can able to say that this is going to be serial shift registers. Just to be recalling that shift register structures, we keep it over here. So according to the input what you are providing to the DIN, the data is going to be getting shifting from one register to the another and one to another and one to another. So we can provide some set of delay to take the input to the output. That's what we can able to see it from here actually, right? So that delaying process can be enabled only by using the SAM, not by in other types of memory architectures. So as like the previous discussion, since your SIPO and PASO, SIPO is providing the higher fastness on the operations, we can able to do this SIPO as your SAM architecture, serial access memory architectures. So as the word to the SIPO, we can see that the data is getting serial in over here, and the output is going to be taken as a parallel at all the registers at the point over here. And this is, we can say, the register 1, so we can say the register 2, and this is going to be register 3, and this is going to be register 3, 3, and this is register 4 we have. Or in other terms, we have flip flop 1, we have flip flop 2, and flip flop 3 is going to be available, and flip flop 4 we can able to keep it over there actually. So when I say the flip flops, so it can able to store one data at a time. Am I correct? Right? So it can store one data at a time. So what is it happening? We can store any data, like it can be 1 or 0, we can store it 1 or 0, we can store the data over here. So it can store and it can able to go for shifting operations. So both is possible when you're going to compare with your normal things. But in the normal, if you're going to take a general memory elements, so it can able to only store the data. It can possibly only store the data, but the shifting operation is not going to be getting possible. But in the case of your SAM, we can store as well as we can able to do the shifting operations. Both is possible. That's what we are doing over here. So after n steps, the present n bit data parallel out is going to be getting out from your structures over there to read the data, or you're going to do the operations of it. and the clock is going to be getting available. Accordingly, we can able to do the shifting operations based on the cycle at which it is going to be getting moving on. So followed by we have PASO. This is also another one approach which can able to provide the faster response for us, right? PASO, right? So here the thing is that, like, based on the shift and load what we are going to provide available, when the shift is going to be getting activated, the data will be start to shift from the one flip flop to the another flip flop like this, through which the mux is going to be getting connected. And based on when the load is going to be getting activated, according to the serial input, the parallel input can be get activated to the all the devices to load. And based on the clock, we can able to do the shifting operations over there. The shift and clock will act as in parallel to do this shifting operation and as well as the loading operations over here, right? And we can see that since we are talking about paralleling, so we can see that all the inputs of your flip flops going to be provided in a parallel, and the output is going to be taken in terms of this serial out. So that is the way in which your SIM is going to be getting acting on the operations. So followed by, for a SAM, we are making use of first in first out. First in first out, and here we are making use of last in first out. So it's nothing but LIFO, and this is nothing but we can call it as a FIFO. We have two architectures, right? So when we normally call this FIFO as a queue, we will call it as a queue. The queue structures can be like this. Okay, let I just draw it in different way because it's just in a grass line, right? So let I draw the structure of queue in this manner. Let's like this. Okay, fine. Right, like this, the queue can be get arranged over here. So as the statement said, this is nothing but first in first out. We are just talking about it. Whatever the data is going to be getting in, that is going to be moving out first. For example, let's say for example first the data is getting moving in here, and here also we can able to follow the shifting operations, and the data will move here, and data will move here, and data will move here, and so on. The data is getting moving at and the moving at out. So we can see that what data is moving out first, whatever it is getting in first, that is going to be acting as an output over here. So that is the reasons why we call it as a first in first out. So if you want to make your next data to be getting in, we can make the queue is empty, and accordingly we can able to write the data and increment the pointer, and one by one we can able to shift the data from this position to this position. At the starting point, the pointer will be pointing out the first location. We will write the first data, and if you want to write the second data, we can shift the pointer to the next one. We can shift the pointer to the next one. The data will be shifted from the first position to the second position. Then we can shift it to the next position so that we can point it to the next position, so it will shift into the next. So like that, so on, the pointer can be get move on your queue, so that we can take output of your data at the end. That is going to be the first in what is it getting into the particular queue. When you compare the last in first out, the last in first out like a stack, the structure of your stack will be like this, right? So here the queue is going to be arranged in terms of the vertical format, you know, when we talk about the stack, right? So whatever the data you want to write it first, we can just put it in the stack like this. So it will be starting from here 0, let's say for example I have 0 1 1 0 1 1 1. So if I want to write this, if you want to read this 0, it will come out at the last only, because whatever it is written as a last, that we can take it as an output first actually. So if you want to take out this, first this has to come out, then this, and then this, and then this, and finally we can able to get your last one, what is it fed in your stack. So that is the reasons why we call it as a last in first out. So it's opting the queue approach as well as the stack approach. So if it is operating with the queue approach, that we can call it as a first in first out, and if it is going to be operating at the stack output, it is called it as comes under the category of your last in first out, right? So that is about the serial access memory. Now we come forward to the CAM, one of the most efficient memory element we can say, or one of the most indigenous memory, as not like your conventional memory architecture, content addressable memory. So we can say that it's going to be a extension of your ordinary memory, that is nothing but SRAM, just an extension but in a different way, like. So here the read and write is going to be as like your normal memory, we are going to do that. But here the thing is that how it is going to become more unique in a sense. Normally if you want to access any data from any kind of memory, you have to provide the particular address, and according to the address line we will search on the address and we can able to read the data what is it available inside. Rather in the CAM device we can provide the data what do you want to read. Instead of address we can able to search as a word which you want to read it back from the memory. Rather to be searching the address, it will be search the content what is it available inside the memory, and it will provide that in which address that particular content is going to be getting available. So that is the way in which your CAM is getting differs from your normal memory architecture, right. So that is the reasons why here we can able to see that match to see which words contains the key, that we will understand on the forthcoming slide. See that how come the general architecture is going to be, we have a CAM block, content addressable memory block is available. So where we have as like the normal memory architecture, we have the read operations and we have a write operation, followed by we have address line is available and data key is going to be getting available, and there is one signal called match, right. Let me see what is match. There is one signal called match, right, that is available. Let's see that how come it is going to be. As I said previously, the CAM is a special kind of memory. How come it is special kind of memory? Why? Because in the traditional memory element, what I said early, the input is address location of your content, that what you want to require, and what is the output will be the data which is present on the data or else the content what is it present on the particular address is going to be coming out. But if you are going to look at the CAM, what I said the previous way, where we can see it over here, the input is associated with something what you already stored in your memory element, that is what the content what is it stored on the memory element. But what is the output? The output is nothing but the location, that is nothing but the address will be the output, that you can easily understand from the structure. See that this is a traditional memory architecture, right. So what you can see that over here we are just giving an input to for the read operations. For the read operation I am giving the address, that is nothing but 0 1, right. At the point of 0 1, what is the data is available, that is the data is available is nothing but like 0 1 1 0 x. So here x is nothing but the don't care conditions, we can say it can be either 0 or it can be either 1. So according to the address line what I am searching to do the read operation, so it just going and verifying with what is it available in the 0 1 and what is the data is available in 0 1, 0 1 1 0 x is going to be getting available, that is going to be transferred as output. That is going to be the traditional memory what we see. Now you come back to the CAM, how it is going to be getting operated. As we said here, rather to provide the address of the data what is it available, we are going to provide the content what is it available inside your memory element. We can see that this we are going to do the read operation again as like your previous case. So what I am going to provide, I am just providing the content. I want the content, or I want to search this content where it is available inside the CAM. What is the content? It is 0 1 1 0 1. So once we given the 0 1 1 0 1, it start to search on your space of the memory where it is going to be getting available. You can see that okay, here 0 is available on this position. Yes, there is a 2 matches available. Here there is 1 match and here there is 1 match. Yes, good. And here we can say that 1 is going to be available next one. So there is here also 1 match, here also 1 match is available. Good. Both are competing now. And here is the 1 is going to be getting available. So we can see that here also 1, here also 1. So far there is a possibility to have this data either in the 0 1 or else either in the 1 0 condition. Let me check the next one. We are starting from the MSB. Okay, we are starting from the MSB. And let me check the next condition. What is it available? It is available 0. And we are verifying that where it is going to be available. This is failed, it is not available. And here is the don't care condition is going to be getting available. That means here it can be a 0 or it can be a 1. Both is possible. But in the case of over here it is 0 is available. It's exactly matching with the content what we are searching, because 0 is available, right? So 0 is available over here, and here also it's going to be either become 0 or 1. Only half of chances we have. So in this case these both will be getting eliminated because that is not going to be getting selected. Now we can see that what is the next one, that is nothing but 1, where the 1 is going to be available. yes, the one is available here, but the remaining MSBs are not matching, so that this is not eligible for us. And there is a don't care conditions of this, all three conditions is going to be getting available, but the remaining MSBs are not eligible to go for to select. But we can see that there is only one, that is nothing but this condition where the remaining 4 MSBs are matching exactly what is it available at the last LSB having X, that can be 0 or 1, that is 50-50 chance is going to be available. That is going to be the maximum match what we are searching for your CAM. So what is the output? We can see the output is showing as 0 1. What is 0 1? The address at which the particular content is going to be getting available. So that is a way in which your CAM is going to be getting differ from your traditional memory architecture, right? So in CAM we are searching about the content, what is it available inside your memory architectures, right? Done. So how come it is going to be the simplified block diagram of your CAM is going to be getting available? We can see that there will be a stored, that's what I said, there will be a stored words will be available. Here we have word 0 to word -1, or else we can say word 0 to word n-1. That will be the size of the words can be get available as an array format, right? And in this followed by we have a such data registers. So here only we are going to feed the input of the content which you want to search on the stored words between w0 to wn-1. And the word which is going to be given, which by the search will be getting into the register, it will store the data over there in the register. The register size will be the word n bit size will be getting available here. It's going to be getting temporarily to be stored and to go for the comparison. And these lines is going to be acting as a search lines. This is going to be acting as what? Search lines, like it has to search in the column wise, the match has to be get identified. On the output side we can able to see the encoder. The encoder is connected with the number of stored words through the match lines. These match lines will be get enabled. This will be get enabled when there is a perfect match is going to be getting identified. When there is a perfect match is going to be identified, a particular match line will be get enabled, so that the respective address will be get encoded and it is going to provide the match location at the output side of your CAM, right? So there might be some question can be get arise. What was the question? If I found more than one match, if I found more than one match, what we can do? If I found more than one match, in the structure we can say that the first once the first match is got identified on your CAM according to the input, that will be deliberately provided as output to your encoder, and the respective match location will be get dragged out from your CAM, so that it won't go for the further searching even there is a matching is going to be getting available in anywhere inside your memory architecture, right? I hope you can able to understand. Once it's identified the first strike on the match, that particular address will be encoded and that location will be get out over there actually, so that we can save the time at which we are going to search on the space where we have. And the maximum length is going to be 36 to 144 bits. You should remember that. And the table size range can be changing from few hundred to 32,000. 32,000 we can able to make it out. And address space can be the with the space of 7 to 15 bits is going to be get possible, right? So there is a two types of CAM we should remember. One is a binary CAM we have, and next one is nothing but the ternary CAM. But in the binary CAM we can see that it's going to be adopt only two logics. Either it will be having the storing the logic of zeros or storing the logic of ones. It stores only logic 0 or logic 1. But in the CAM there is a third logic is also, that in ternary CAM we have the third logic also. What was that? That is nothing but zeros there, and we can have ones, and we have don't care conditions. As we discussed earlier, don't care conditions we can say either 1 or we can say it's going to be a 0. So that is another one possibility which makes the CAM to be operated in a more faster way, because if MSBs are matching, one of the MSB or one of the LSB is not matching with all, but one of the match available with the value of X, we can take that as a match as output. Why? Because we can, that can able to be as a 0 or can be a 1. That's what the ternary CAM can be more useful for us rather to go with the binary CAM. And what is available sizes available? Like it can be available in different sizes like 1 MB, 2 MB, 4.7 MB, 9.4 MB and 18.8 MB is possible in the things. And it having like the entire structures multiplies 36 bits rather than to go for the 32 bits. So these are all the typical things about the types of CAMs in a market, right? Let me come for the advantage part. They associate the input with their memory content in one clock cycle, of course, and they are configurable in multiple formats of width and depth of the such data what is it available. And CAM can be cascaded into increased size of the lookup tables. We can do the cascading operation between one CAM structure to the another CAM structure, and we can add n new entries into the table to learn how it is going to be getting searching on it, and it's one of the appropriate solutions for the high speed operations that I said early, right? And when I say the drawback, the cost of the CAM for the fabrication, like the unit of the CAM is going to be more costlier because it's required more than SRAM cells, more than the conventional memory cells. It required some extra elements like encoder data and the registers to support this content addressable searching. So it's occupy the larger area, it's having the more number of transistors, so it's increasing the cost of the CAM devices over there. And relatively it is going to be occupying the larger area because of the huge number of transistors due to the extra components which is required for the CAM to make it perfect to operate it. And ultimately when the transistor number is getting increasing, we can say that the power dissipation also is getting increasing over there. And there are some issues like interfacing and simultaneous tabulation updation, maybe that can be get avoided once we are going to follow a standard cascading approach of your CAM. And see that here a CAM array is showing for you, that is nothing but 4 cross 4. You remember always the CAM will have a n cross n array. You may remember about your ROM what we studied, where we studied about m cross n. So the m is going to be indicating the words, m is indicating the words and n is indicating the n bits of words. I hope you remember, we seen in the ROM structure. But in the case over here we are using only n cross n, that means we are going to follow like a mesh like structure. We will have equal number of CAM cells will be available in both in the row as well as in the column. So we can say that this is going to be 1, 2, 3, 4 in terms of if we have 4 rows are available, same way we can, so 4 rows are available, same way we can able to say 1, 2, 3, 4 columns going to be getting available over here. So it's going to be following a n cross n structure, and according to the match is going to be found, either the match 0 or match 1, match 2 or match 3 can be taken out according to the data what is it available inside your CAM, right? So that's it. So just be seen how the SAM and CAM is going to be unique from your traditional memory architecture. So remember, SAM is serial access memory device and it doesn't have any kind of address lines not required, and it is going to be adopting the SIPO and PASO for the simple architecture to follow. And CAM it's different from your traditional memory architecture because it's not using address to search the data, rather it is going to be using the content what is it available in the particular CAM device to access the address of it particular memory devices, and it is more faster when you're going to compare with the traditional memory architectures, right? Thank you so much, and let me meet in the next session then. Thank you.